Hi everyone, good afternoon. I am Fen Liu, a visiting scientist at Riken AIP and a lecturer in University of Melbourne. Today, I will host the 15th Trustworthy Machine Learning Young Scientist Seminar. Before the main talk, I will briefly introduce our Riken AIP Center to our valuable guest. The full name of Riken AIP is the Riken Center for Advanced Intelligence Project. AIP was founded in 2016 as a research center for the next mixed AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance AI fundamental technology and its real-world applications. AIP also encourages the collaboration with various researchers and engineers in the related field. And we would be grateful if you could visit us in the Hombashi office in Tokyo in near future after the pandemic. Next, let me introduce our guest, Jonas from Max Planck Institute for Intelligent Systems. He's currently a fourth-year PhD student in MPI, supervised by Professor Bernhard Schokov. His research interests include the potential of defining machine learning models like quantum computers and kernel-based hypothesis test, and how they can be made as data efficient as possible. Today, he will give us a talk regarding how to learn powerful two-sample test. Welcome.
Thank you very much. All right, let me start sharing my screen. Okay. Yeah, it's my great pleasure to have my first time in Japan today, although it's online. But yeah, physically in Tübingen, but virtually with you in Japan today. And I will talk about how we can learn powerful two-sample tests. And as Feng already said, I'm at the Empirical Inference Department at the Max Planck Institute for Intelligent Systems, and I'm also a member of this International Max Planck Research School for Intelligent Systems, which is kind of the graduate school I'm in. I will talk about two papers. One was a NeurIPS 2020 paper, the title Learning Kernel Tests Without Data Splitting, and the other is a more recent one from AI Stats this year, which is called the Witness two-sample test. And both papers are with the same authors, which is me and Vittavat, Bernhard and Krickamol. And when we started this, we were all at the Empirical Inference Department. Vittavat by now is at Google Research. All right, let me start by introducing two-sample tests generally. Like, what is it about? And the idea is that we want to test the null hypothesis that two distributions are the same. So we have distributions P and Q, and we want to know, are they the same? And we do this based on data, where we are given two samples, one drawn IID from P, and the other one drawn IID from Q. So for example, we could have this one-dimensional data sets where I visualize it as a histogram, and now based on that, you would like to decide whether P equals Q. Or you could have, say, image data sets where you're interested in, like, is the distribution the same on the left side? Maybe you trained a model on samples from P, and now you deploy this model in the wild, and you want to know, is the distribution still the same, which is kind of like distribution shift or covariate shift. And we will be concerned with good tests or powerful tests. And the most important thing for a good test is that it should control type 1 error. That is, when the null hypothesis is true, so when P actually equals Q, we would like that our test only rejects very rarely with a fixed rate, usually set to, like, it's called a significance level, and we usually, a default value is 5%. And once we ensure that, we would like our test to be as powerful as possible and minimize the type 2 error. The type 2 error is defined as when P is unequal Q, that we failed to detect this. So we would like to make this rate as small as possible while still guaranteeing type 1 error control. Now, how do we test? Obviously, it's a bit hard maybe for a computer to just ask, like, are the distributions the same? So the way we will do this is we will define a test statistic that will take the data as input and compute a real number. And then we will compute the p-value of our observed test statistic, which is the probability that we would observe a value of the test statistic at least as extreme as what we observed when the null hypothesis was true. Okay, and obviously this will depend on both the data that we saw, this p-value, but also on the choice of test statistic. And that's what we're going to be concerned with. We want to define test statistics such that the p-values are small and we reject as often as possible. What we do is we reject if the p-value is smaller than the significance level, and therefore we will control the type 1 error at the rate alpha if we manage to correctly estimate these probabilities here. Now, how could this look like? For example, if you know a lot about your data or you can make strong parametric assumptions, then you can easily define a test statistic. For example, in this example, I could tell you that actually the data comes from two normal distributions, that's for sure, and both have equal variance. And so only the mean could differ, and let's make it even stronger and say we only assume that P could have a larger mean than Q, but never smaller. So in that case, our null hypothesis P equal Q, which was kind of abstract, reduces to something very simple, which is testing whether the means are equal. And as a test statistic to test this, we could, for example, compute the mean of the two samples, the empirical means, and compare them. In this case, for this particular data set, what you would get is something like 0.278. And now for this simple case, under these strong parametric assumptions, we could also compute the distribution of this test statistic under the null hypothesis. So when P equals Q, then this difference in means test statistic is normally distributed with mean 0 and variance given by the sum of the sample variances. So in this particular case, I chose 100 samples from each distribution. So I get 1 over 100 times 2, and I got variance 1 over 50. And then I can compute the p-value as the probability that under the null hypothesis, the test statistic would be larger than what I observed on my empirical data. In this case, it's just given by 1 minus the cumulative distribution function of the value of the test statistic that I observed, normalized by the sample size. And for this particular data set, I would get it, it's something like 2.5%. So for example, if my significance level was at 5%, I would reject based on that. But what about more complicated data sets where we can't make such strong assumptions? Here, one way is to use a very flexible method upfront, for example, MMD, and we will come back to that. Or the other way is to use a two-stage approach, where basically we split the data, test the second stage on the held out data with this learned test statistic. And I think this is quite an intuitive approach to two-sample testing, which is also maybe the way you would approach it as a human. For example, if you wanted to know whether this die that you're rolling is fair, you would probably roll it a few times, and then you would kind of look at the statistics and be like, maybe there's more sixes than there should be. And then that would be your hypothesis, and you would roll again a few times and then actually test whether you see significantly more sixes. What I will show in this work is that actually sometimes you can even do this without data splitting. So you can, in principle, use the same data to learn the test and do the test, but you will have to be careful to get correct p-values. One nice thing about two-sample testing is that there's a relatively simple way to simulate p-values. Because as we will see, or what is kind of happening is that when you have complicated test statistics, it might not be so easy to estimate or like to get the p-value in close. And the idea here is that under the null hypothesis, we can basically think of our two samples as being like one big sample that came from the distribution P, and then which was randomly split into X and Y. And so the idea is to simulate the null hypothesis. We can just basically merge the two samples that we have. We can permute them and resplit them and recompute the test statistic each time. And then we like, okay, let's just do this. So this was our original partition of the data, and we computed that tau is 0.278. And now we shuffle and we resplit and we recompute tau. We do this a few times, over and over again, say 300 times. That's just an arbitrary number at this point. And then we can plot the empirical distribution function of this observation, and we can locate the value of the test statistic that we originally computed, right? This was this 0.27 something. And then we can just take the p-value as 1 minus the empirical distribution function at this point. And this approach kind of works no matter how complicated your test statistic is. Okay, let me now introduce the maximum mean discrepancy as one, let's say, big step in machine learning-based hypothesis testing or two-sample testing. I think the best paper is this JMR paper from 2012, but I think the idea is already a bit older, and it uses reproducing kernel Hilbert spaces, which I'll just put here, but I think most people know them. So I'll just continue. The maximum mean discrepancy is defined as the maximum mean discrepancy. So mean discrepancy just means we have a function and we compute the difference in means under P and under Q. And we take the maximum mean discrepancy over a unit ball in the RKHS, in the reproducing kernel Hilbert space. And we can rewrite this in terms of the kernel mean embedding. So the kernel mean embedding is basically an embedding of a distribution in the RKHS. And then the MMD, we can write these expectations as inner products of a function with the mean embeddings. So this difference in means just becomes the inner product with the difference of the mean embeddings. And we can define a so-called witness function, which is basically the function that maximizes the mean discrepancy. And as you can see, since we optimize over the unit ball in the RKHS, the function that maximizes this inner product is the one that points in the same direction as the difference in means. And that's why the witness function takes on this form. And so we can rewrite also the MMD just as the norm of the difference in means of the mean embeddings, or if we will take the squared MMD, it's just the inner product of the difference in mean embeddings with itself. And the squared MMD, that will be the basis of test statistics that we will consider in the following. And one nice thing about using RKHS is that if we have a characteristic kernel, for example, a Gaussian kernel is characteristic, then the mean embeddings equal if and only if the distributions are the same. So basically, every different distribution gets mapped to a different mean embedding, and hence we can take this actually to detect differences in distributions. And what we will basically test then, now we have something that is again computable. The null hypothesis now is that the squared MMD is 0, and we test against the alternative that the squared MMD is larger than 0. So now we will have to talk about how do we actually estimate the MMD in practice from data. And therefore, let me rewrite the squared MMD like this. And now we basically have to estimate it with our data. And one way to do this is to use a minimum variance unbiased estimator, which basically, is an unbiased estimator with the smallest variance. So if you have little data, that's what you should do. But note that it basically takes quadratically many operations to estimate. And there's another estimator which only takes linearly many steps, which thus has a larger variance, but is faster to compute. And this basically starts from the second line up here and just basically takes every sample only once. So you kind of see here also that there can be trade-offs between runtime and significance, because with the use statistic, you're likely getting more significant outcomes of your test, but at the cost of a higher runtime. And what turned out over the years that when you do to sample testing with kernels, actually it's very important to have a good kernel. And I think initially people mostly used heuristics like the median heuristic to define the kernel. But it turned out that if you actually take some data apart to first optimize the kernel and then use it for a subsequent test, this can actually increase test power. And one early work that did this for the linear time estimate is this NeurIPS 2012 paper, and a more recent work that does it for the use statistic test. I think there was also one work even prior to that, was this Asymptotic paper 2020 by Feng. And what we'll show today is basically that in case of this linear time test, I can learn the test statistic even without data splitting. And in our experiments, we will see that this even leads to more significant results or better test power. And for the second case, I will argue that instead of learning a kernel function, we could also consider directly learning a witness function that gives us optimal testing properties. And this will be based on the second paper. Okay, let's start with the first one. and go back to the linear time estimate. So the linear time MMD estimate has this nice property that if we define basically set as like this for tuple of our data points, then we can just write the estimate as an empirical mean of a function h evaluated at set I. And this will be our test statistic. And what we then have is that this test statistic will be asymptotically normally distributed. So it will converge to a normal distribution where the mean is given by the actual, like the population value of the squared MMD, and the variance is given by the variance of this estimate. Now, what does it mean? So, okay, we have that it's asymptotically normal. So that's what I plotted here. And now we can relatively easily compute an analytic test threshold that controls the type 1 error. So basically we can control always, we can reject always if tau is larger than T alpha, which is chosen such that a normal distribution with 0 mean basically has exactly 5 or alpha % of its weight in here. But the cool thing is now we can even analyze asymptotically how many type 2 errors we will make. And therefore we basically look at the distribution under the alternative hypothesis, which is now centered somewhere here. And we can now look at what is the probability that our test statistic under the alternative hypothesis is smaller than the test threshold. And this is given by this function here, which now means that if we want to maximize the test power, or equivalently, if we want to minimize the type 2 error, we should make this function as small as possible. And hence, we should maximize this signal to noise ratio here. So square root of n, it's given to us, we can't optimize that. But what we can influence is the value of the MMD divided by its standard deviation, and this will depend on the kernel that we choose. And yeah, one easy way to do this is based on data splitting, where you first take data apart, you optimize the signal to noise ratio, and then you test with the other part. But this, of course, like leaves less data for testing, right? And how much data you have for the test obviously also depends the test power. So what we are going to do is we will take all the data for a joint estimate and then optimize the test based on that. And the idea here is that we basically will work in a framework where we say, okay, we will select a hypothesis test based on some event. And the difficulty here is to correctly control the type 1 error rate. So again, the type 1 error rate is the probability that we reject under the null hypothesis. And if we consider a possible set of different tests, then we basically can write this as a sum where the probability of the event AI happening, which makes us use the test tau I, and then the probability that what we observe is larger than the ith threshold. And the important thing here is that the threshold now is conditioned not only on the null hypothesis, but also on the event that we selected the test. And that's going to be the difficult part to take care of. And it also, this formula also kind of easily illustrates why data splitting is so convenient. Because in data splitting, the event that you compute or that you test to select which test to use is independent of your test statistic that you compute afterwards, because you use two independent splits of your data. So here, the test statistic does not depend anymore, or it's independent on the selection event. And therefore we can just basically pretend as if this was just a test that we chose a priori. And it's very easy to compute thresholds. And we will have to, if we take the same data, we will have to derive a distribution that takes this conditioning into account. And to do this, we will start with D candidate kernels, so just a number of candidate kernels, and the linear time MMD estimates as test statistic. And I will now show how we can derive these asymptotic condition distributions. So what happens if we have a number of linear time MMD estimates, then we can basically write them as a vector. And this vector now is asymptotically normally distributed again, with basically the mean given by the population MMD values of the various kernels. And the covariance is given by the covariance of these MMD estimates of the different kernels. And what I will do is I will define a normalized test statistic where basically I project my vector of different test statistics onto a one-dimensional object, which corresponds to linear combination of kernels that I consider, and I will normalize it by their variance. And then I can basically check which one has the maximal test power. And if I do this and I allow for arbitrary linear combinations, then I basically will have to optimize the signal to noise ratio that we derived. And if I allow for arbitrary linear combinations, then actually I can find the best direction, so to say, or the best linear combination in closed form, which is just given by taking the inverse covariance matrix and multiplying it onto the mean vector. But this is a population quantity that I'm writing down here. So basically the procedure will be, we will first optimize beta with some estimate and then take the corresponding linear combination as test statistic. So in practice, we don't know the mean, of course, like we don't know the MMDs, otherwise we wouldn't need to test anything. So we optimize this with our linear time estimates. And then I will call this beta infinity when I take the empirical version beta Wald, because there actually turns out to be a classic hypothesis test in that way. So now I took tau, I compute the optimal linear combination based on tau, and then the test statistic will be basically the projection of our vector of test statistics onto this direction, and I will normalize it. And in this case, you can actually write it as sigma to the -1/2 times tau. Now, if you look at this, we basically have done a two-stage procedure, right? We first optimized and then we used an optimized test statistic, but we were actually able to write this down in closed form. So you can actually think of this particular case as just having defined this test statistic upfront. So we actually don't need to do the conditioning here, but you can directly derive the null distribution of this joint test, basically. And under the null hypothesis, we have that taking the covariance to the -1/2 times our test statistic actually follows a standard normal distribution. Okay, and it's d-dimensional, and so the norm of this quantity is distributed according to a chi distribution with d degrees of freedom. Okay, so for this particular conditional hypothesis test, we were actually able to derive the closed form solution without really taking the optimization really into account, because you could do everything in closed form. And it turns out that this is a test statistic that has long been known. However, what we ignored here is that we are only testing this one-sided alternative, because we're only testing whether the squared MMD is positive. And we know that it can't be negative because we're working with the squared MMD. And so what we will do now is we will, or maybe I should go back once. So maybe someone wondered about this constraint that we constrain the values of beta to have norm 1, but that's not an important constraint because this whole fraction here is independent of rescaling of beta. So the test statistic will always be the same essentially if I take beta times 5 or anything like that. And so to make the solution unique, we just constrain it to the unit ball. And now when we know that we're only testing this one-sided alternative, we can use a one-sided test. So generally, if you have some information and you can constrain your alternative hypothesis, you should generally do that, because testing against a less general alternative usually gives you more test power. And ignoring some fine print, we can basically write this now as just considering betas which are also in the positive cone. And now things actually become a bit more complicated, and that's where the main theorem of this paper comes in. So again, under our assumptions that tau follows this asymptotically normal distribution, and we're talking here under the null hypothesis because we're concerned with p-values under the null hypothesis. And basically beta star will now denote the optimizer in this equation 1 here. And we will take this I will call this active set, this calligraphic U, which basically contains all the directions where beta star U is unequal to 0. So all the directions that are not forced to 0 by this constraint essentially. And L will just denote the number of directions that are active. And Z will become clear in a second, but it essentially projects tau onto onto something that is orthogonal or independent of the projection onto beta star. And what we find then is that if exactly one direction is active, then the distribution of this maximized test statistic, so recall what we do here is we first maximize beta, and then we take this whole maximized test statistic to test, and we take the same data. If one direction is active, then what we find is that the distribution under the null hypothesis conditioned on the maximization, so conditioned on that we chose exactly this active set, will follow a truncated normal distribution, which is basically truncated from below and then renormalized. And if more than one dimensions are active, then we can show that so if L dimensions are active, we can show that the maximized test statistic follows a chi-distribution with L degrees of freedom. So kind of similar to what we saw for the Wald test. And I will try to illustrate this with a sketch. And this is for the case that the covariance is the identity matrix. Okay, in this case, it's relatively easy to understand because now Z is basically just orthogonal to beta star. And let me see. Yes, so in this case, it's also relatively easy to understand the maximization, right? If tau falls in this positive irrtant, then we will just take beta star as the direction of tau, basically. Whereas if it falls in this red region down here, we will set the second coordinate to 0 and consider beta star to be just the first coordinate. And similarly here in the orange part. And for a particular example, let's think that tau hat is down here. Now we force the second coordinate to 0 and take beta star just as the projection on tau 1. And Z hat is now independent of beta star. And basically, so that's why we can condition on Z hat without affecting beta star times tau 1. And now given this Z hat, what you can see is that if the projection onto the first axis was smaller than this V minus, which is this threshold, then we would actually have picked another beta star, right? In this case, if we went below this threshold, we would have selected tau 2 as test statistic. And this is the reason why under the null hypothesis now, instead of following a normal distribution, as it would be in the unconditioned case, it follows a normal distribution that is truncated exactly here. Because basically knowing that we chose beta star to be the first coordinate means that we know already that the value of the test statistic was larger than this threshold. And that's the reason for this. Had in the first octant, then basically this whole constraints are inactive. Like they don't even matter because it's exactly, we would exactly pick what we would have picked without constraints. And that's kind of the plausible explanation why in this case, the test statistic follows exactly the same distribution that we saw for the Wald test. So remember, that was chi-d. And now if no constraints are active, we get also again a chi-d distribution, or it turns out that if only a few constraints are inactive, we have a chi-l distribution. So basically now we have two distributions from which we can relatively easily compute test thresholds or p-values, because you can just use any standard package to compute the CDF of these distributions. Now let's see how this works out in experiments. So what we do is we consider different data sets and a different number of different base kernels. Our one-sided test that we're proposing against the Wald test, which was this original test, and the prior data splitting approach, and also the naive one. So with naive here, I mean that I use the same data for learning and testing, but without accounting for it. So the naive approach actually is a test that does not work because it does not control type 1 error, but I just plotted it here for convenience as well. And what we see is that actually our one-sided test always performs best compared to these other tests. Like splitting the data seems to be less efficient than using all the data for learning and testing, and also using a one-sided test as opposed to a Wald test can give you some advantage, although arguably here it's relatively simple. But since our whole approach does not cause any like large computational costs, so it's essentially as computationally efficient as the data splitting approach, I think you can just use the one-sided test. Okay, so let me summarize this first paper. So what I showed is that it's in principle possible to use the same data for selecting the test and also testing its significance, which is, I think, quite remarkable, because at least before I started working on that, I was very sure that you should never do that. And then we also generalized this existing post-selection inference framework where this kind of built on, and that's just because our theorem is applicable also in other settings that are not related to hypothesis testing. And we saw that also empirically, we can improve the performance without having more computational costs. But the limitations are a bit that this only allows us to consider linear combination of base kernels. And it's also only reasonably applicable in a regime where we have a lot of data, because we're using this linear time kernel, this linear time MMD estimate, which is relatively inefficient in terms of information. And these limitations are kind of there because we strongly use this asymptotic normality under the null hypothesis. That's important. So also under the alternative, but here we also heavily use that under the null hypothesis, it is asymptotically normal. And if you drop these limitations, then you don't have this asymptotic normality under the null anymore, probably. And then I really don't know how to generalize this theory. So that was also some of the motivation that led to this second work, which I will talk about now, which basically went back to this squared MMD estimate, which we look at now again. And we will rewrite it once more, and we can basically rewrite the squared MMD as the difference in means of the witness function, where here we'll use the unnormalized witness function. So that's the function that we introduced in the beginning. So just now it becomes very apparent that the MMD is a mean discrepancy. It's a difference in means of some function, which is called witness function. And the witness function is chosen in the ArcHS in the standard approach of MMD. And now let's go back to these estimates really quick. So I introduced the U statistic estimate before, but I will also introduce a V statistic estimate, which is not unbiased anymore, but slightly biased, but which allows for a slightly simpler interpretation. So basically, if you also include these self-correlated terms here, we get a somewhat simpler expression, and we can actually write this this estimate now as the empirical difference in means under the two samples of the empirical witness function. So HK of Z is just the empirical witness function. So you can actually also think of this as a two-stage approach. You take your data, you first learn the witness function, which is just given like that, you estimate it, and then you take its difference in means as a test statistic. That's what MMD actually does. So you can even think of it as a two-stage procedure that uses the same data for learning and testing in a very simplified manner, which is one reason why computing p-values is a bit more involved here. Okay, and now, as I said in the beginning, kernel optimization is quite important. And I just boldly copied a screenshot here from Fang's paper from ICML 2020, which basically considers the asymptotic distribution of the unbiased MMD estimate, but I think it's roughly the same for the biased one. But what you see here is that also this estimate is asymptotically normal under the alternative hypothesis. So you basically have that your estimate converges to its population value, and you have some variance term. And what they show then, or it's actually, I think the first time it was shown in this paper of Sutherland et al. In 2017, is that if you want to optimize test power asymptotically, you should choose a kernel that optimizes this criterion J here, which is also some kind of signal to noise ratio, which is just the squared MMD, the population value, divided by the standard deviation. So it's not an error that we have a square here, but not here, because this is actually standard deviation of the squared MMD estimate. And now the approach would be to split the data, optimize the kernel by optimizing an empirical estimate of J on this held out data, and then take the standard MMD test on the testing data. Okay, so now I will use some color. As I said, we will split the data into training and test sets, and we will use the training sets to optimize the kernel function via this criterion J, which gives us a kernel that depends on the training data. And now the approach proposed previously was basically to use this kernel and use the test data to compute the test statistic. And here, as I said, you can think of MMD as first estimating the witness function with the data and then testing with the same data. So here you have a witness function that depends on the kernel that you defined in the training data, but then depends also on your test data. Okay. And my idea was basically, well, what if after the optimization of the kernel, we reuse the training data once more to directly estimate the witness function in this optimized RKHS with the same data. Okay, so that's what I kind of propose. And now the nice thing is that our test statistic now is just an empirical, like a difference in empirical means of this witness function that now entirely depends on the training data. So now this witness function is completely independent of our test data. And this will be a nice property that we will use in a second. But now let's quickly peek at some experiments. So when I took the implementation on these two data sets of Feng et al. Or Liu et al. And I just basically, after the optimization, I estimated the witness function with the training data. I observed that I could, in some cases, achieve better performance than before, which was kind of some motivation to look more directly into it. And I also want to emphasize that this doesn't involve any additional computational cost. So let's look at this a bit more generally and look at this test statistic. So the idea is now to really, in the training stage, directly use a witness function and directly optimize this witness function with the training data. And the test statistic that I want to use ultimately is the mean discrepancy of this witness function. So that's, just to go back quickly, that's exactly the same form that we have here. Just now, I'll basically not first optimize the kernel and then take its witness, but I will directly optimize the witness. And to do this, I will also look at the asymptotic distribution of this test statistic. And what we find here is that this asymptotic distribution is again normal both under the null and the alternative hypothesis. So here again, it's also under the null hypothesis asymptotically normal. And this is something that we have seen before, right? So let's quickly go back and recall what we did on slide 12, where we said, well, if we want to optimize the test power in such a setting, we should optimize the signal to noise ratio. So in our case, the signal to noise ratio is just the difference in the means pool standard deviation of the two distributions. And what I show, or what we showed in this paper, is that if we want to optimize this over an RKHS, over reproducing kernel Hilbert space, so we want to find the optimal witness in an RKHS, we can do this via kernel Fisher discriminant analysis. And I also provided a, let's say, sped up implementation of that. And what is also nice in this approach that we can, for example, use cross-validation in the training stage to basically choose which kernel should we use for this, or which RKHS should we use, and which regularization should we use when we optimize this. And it's relatively simple because we're again in this data splitting procedure, right? So whatever you do on the first stage doesn't affect your type 1 error control, which is entirely dependent on the second stage. And that's basically how, let's say, the algorithm works. So basically you get your data, you split the data into training and test sets, then you maybe do some cross-validation, and then you optimize your witness function, which in this case we propose to use KFDA, and then you run this test basically with the witness function and your test data. And to run the test, you just compute the mean discrepancy of your witness in the test data, and then you simulate your p-values via permutations. And what I want to emphasize here is that I actually have to evaluate this witness only once. So here I basically take an array and I first compute the witness for all data points in my test data set. And then I just have to permute these witness values. So I don't need to re-evaluate the witness, which of course makes it then relatively cheap to compute these permutations. Now in practice, let's see how this works. These were the two plots that I showed before, and now I'll add some other baselines and also the KFDA witness. So here, taking this relatively simple KFDA witness also gives very good performance, and here just some other benchmarks. Okay, let me quickly summarize that, and then I will quickly touch upon another point. So I basically motivated that we should, or that one way to do two sample tests is also just to take a witness function and take its mean discrepancy as test statistic. And in order to find this witness function, we should maximize the signal to noise ratio criterion, which optimizes the asymptotic test power. And here's just a quick comparison of the witness test with the optimized MMD. So both optimize the asymptotic test power via signal to noise ratio criterion. And the testing runtime is a bit better in the witness test because the test statistic is only difference in means. So this is just linear, whereas in case of the MMD, you have to compute quadratically many terms. But also here, you don't need to recompute the kernel evaluations every time. You can also just store this kernel matrix and then permute the entries there. So in practice, this is also relatively fast. I would argue that understanding this witness test and its asymptotic properties is slightly simpler than understanding everything about MMD and its asymptotic test power criterion. And the performance, I just put boldly here that the witness test performs a bit better than the optimized MMD, but I think this also will have to stand the test of time, to be honest. Maybe one more thing that I wanted to mention here quickly, and I wanted to strengthen the relation a bit of this witness to sample test and the MMD with optimized kernel. As I said, this is the MMD witness, and the J criterion that prior work used to optimize the kernel when they did normal MMD is this criterion here, which basically squared MMD divided by its standard deviation. And what we showed in our paper is that you can directly relate it to the signal to noise ratio that we used of the MMD witness function of the kernel K. And now, what does it mean? So for MMD, what people did is they optimized the kernel to maximize J. And basically, one way that I think of this is if we do this, we are actually maximizing the RKHS such that the MMD witness function in this RKHS would be the optimal witness for a witness to sample test. Okay. So we basically we optimize the kernel, but all that we actually care about this kernel is actually its witness. And so, like, say a bold statement is somehow that instead of taking this detour over optimizing the kernel to maximize the properties of its witness function, we could also directly go for a witness function. And that's kind of the bottom line of this whole paper. Which is something that, I mean, there's like, we don't have an analytic proof or something like that it's better. And I'm not saying that it's always better, but it's just, to me, it seems a bit more direct. Yeah, and with that, I would like to conclude. Maybe just a quick recap. And the quick recap is that in practice, to sample testing on complex data, it's reasonably done in a two-stage procedure. And I showed in principle that data splitting is not possible, it's not necessary if you have, for example, this linear time MMD estimates, but this is a bit limited. And so in the second part, I talked about a case where we actually split the data. And here I motivated that directly optimizing a one-dimensional witness function can outperform the more indirect approach of learning a kernel. And I think it's conceptually a little bit simpler and performs well. So we will have to see what the future brings about these methods. And with that, I would like to thank you for your attention and also particularly for the opportunity here to present my work. And if you have any questions or discussions or anything like that, you can always reach out to me via email. Thank you very much. And of course, I'm happy to take questions if there are any.
Yeah, thank you, Jonas. That's a really great talk. Yeah, I noticed there are 2 questions in the chat box. Yeah. Have you seen that?
Oh, I just saw them now. So
Yeah.
the one was, excuse me, can I say kernel mean embedding is a way of calculating the mean? Um, so let me quickly go back. There's a lot of slides. So the kernel mean embedding, I mean, in the simplest case, if you had a linear kernel, then indeed the kernel mean embedding would correspond to the mean of your data. But the kernel mean embedding can have like more things. So basically, you could also think of like having the mean of like your variable and the expectation of your variable squared, or your expectation of your variable to the power 3, and you basically embed all of these. So this can be an infinite dimensional embedding in the RKHS, and it with a characteristic kernel, it basically embeds all the information that you need to know about your distribution. So you, for example, it could be all moments of your distribution if you tweak it in the right way. Yeah, and that's also why like just taking the mean obviously is not enough to distinguish arbitrary distributions, but you need to basically take all properties of your distribution into account. Yeah, feel free to follow up on that. And the other question is, you mentioned in the beginning that hypothesis tests can be used to detect a covariate shift. For example, Q is a noise contaminated version of P. I would like to know if hypothesis test or its related methods can be used to calibrate or correct Q back to P. So that's an interesting question, and I'm not aware of any way to do that, but I should say that one interesting way, or one interesting thing about the 2-sample tests is that you can basically try to interpret the differences in the distributions. So also prior work, also done by Wittawat, has basically showed that for some hypothesis tests, you can look, after you did the test, you can basically look which are the most prominent examples from P and the most prominent examples from Q. And if you do this, and then you, for example, in case of images, you basically see that these typical examples from Q, they have a lot of, let's say, white noise in them, or a lot more white noise, whereas the typical examples of P, they are very unnoisy. Then you could at least understand what where the difference in the two distribution comes from, or what kind of shift you saw. And yeah, I mean, it's kind of hard to invert noise, I guess, if you don't know for the exact sample like what the noise was, right? But at least that's one way to interpret the difference in the distributions. Yeah, and yeah, sure, you can have links of these works. Maybe it's best if you just send me an email afterwards, so that I can just follow up with you on that. Cool. Thanks for the questions. Very good questions. Yeah, and maybe I should say, in case of the witness also, the way we train the witness, so we train the witness such that its mean under P is larger than its mean under Q. So once you have your trained witness, you can actually also take your data and push it through the witness, and then just look which examples got the largest value under the witness. Those are the very prominent examples from P. And which examples got the smallest value under the witness, and those are the most prominent examples from Q. So also here you could, in principle, interpret your results.
Okay, yeah, thanks. Thanks, Jokai, for the great questions. Yeah, I also had a general question about this two-sample testing. Because in the adversary data detection, or like out of distribution data detection, in the detections they intend to design like a score function to judge if this data, just the one data, is from the OD distribution or is from adversary data. Yeah, so it's kind of different from our normal setting, right? Because in the TrustML test, we have two batches, at least two
Mm.
batches, yeah, with some data inside. So, yeah. So do you have any like comments about these things, like connecting the testing methods and the detection methods? Yeah.
Mm. It's kind of funny because I had a similar question recently also from someone else, and
Yeah.
I don't really know, but I mean, like, if you have some way of like basically characterizing like the distribution of your training data, I mean, it's more like an
Mhm.
outlier detection, right? You would be more like,
Yeah.
is
Yeah.
this one data point like far away from the distribution that I trained on, if I understand correctly? I'm not quite sure how we can do it like do this with a two sample test, to be honest.
Yeah, I think maybe the weighting function you mentioned here can be considered as a score function, maybe, right?
But then I would have to train it, right? I would have to basically
Yeah,
have
yeah,
like my
that's a
my real examples, and then I would have to have unlikely examples and kind of
yeah,
try to train the witness on that. Um, which, yeah, as I understood you, it's more like, okay, I have a single example and I want to know, is it
yeah,
exotic or not? Which seems a bit harder,
yeah, very hard. Yeah.
strictly
So
harder maybe.
yeah, I'm thinking if the weighting function, if we train the weighting function with like the like in distribution data and other like we generate some out of distribution data, right?
Mm.
To try to train some weighting function, it may be used as a score function for the detection. Yeah. Yeah,
Something
that's
like that. That
yeah,
might
it's
potentially
just
work.
some ideas. I just think about it. Yeah,
Uh,
yeah, okay. Yeah. Are there any questions from audience? I think there. Oh, Joe
Oh,
can
there's a final
also.
stupid question. Why can't I simply control the type 1 and type 2 errors simply by choosing a very small significance threshold? So when you choose a very small significance threshold, then you actually make your type 1 error smaller. That's true. But your type 2 error will spike because the type 2 error is basically um, that your p-value is smaller than your significance threshold. So basically making the significance threshold smaller decreases type 1 error, but it always will increase type 2 error. So that's why there's this trade-off. And we have to find methods that at a fixed significance threshold optimize the type 2 error.
Okay.
Cool.
May I ask a question?
Ah, yes, please. Go ahead.
Thank you very much for very interesting talk. My question is about the optimization of kernel.
Uh-huh.
The kernel mean embedding depend on the kernel.
Yes.
So what kind of candidate kernels do you expect? In the
So yeah, so I mean, Feng is probably the better expert on this, but maybe I can quickly comment on it. Oh, I probably don't need slides for that. But I think the simplest thing you could consider is what I considered in this linear time estimates, that you have, let's just say, a finite number of candidate kernels, and you optimize linear combination of these kernels. Because
right,
if you take a sum of kernels, it's again a kernel.
right.
And that's very simple, but also very limited. And so
Yeah,
what Fang did
yeah.
in their paper, in their ICML paper, they considered a deep kernel, for example, where you
Uh-huh.
learn a deep representation and then you squash it through a kernel function.
Uh-huh.
And then you just like by gradient descent optimize this criterion, which of course gives you much more flexibility. But let's say it's also a bit harder to then completely understand what's exactly going on as usual.
I see. Thank you very much.
Welcome.
Yeah, thank you for the good question.
I mean, feel free to add on this thing if you feel like I said something incomplete or
Yeah. Okay, I think maybe there are no more questions. Yeah, if you have more questions or like the interest for this TrustML testing works, you can just email Jonas. Yeah, he's yeah, definitely an expert in this area. Yeah. Okay, cool. Yeah, thanks for giving us this great talk. Yeah.
Thank you for the opportunity.
Yeah.
And
Bye-bye.
see you soon.
See you.
Bye.
Bye-bye.